the network is spread out its decision making, so it's spread out along multiple points, and instead of one central authority, there are several nodes or agents that have the power to make decisions. And this setup, of course, reduces the resilience and on a single point, and also enhances some security and reliance. And then there is, and then there is the distributed network, where control and data is fully spread across all nodes in the network, and every node operates independently and cooperatively, and they have no central authority. Okay, so decentralized optimization then, that is an important concept in various fields, so computer science and engineering and also economics and things like that. And it involves solving optimization problems in a distributed manner, where the decision making is spread across multiple nodes. Decentralized and distributed networks are closely related, and they often overlap in their application and principle, and many times the two are very closely related in terms of optimization. And sometimes some even say that decentralized optimization is a special case or a subset of distributed optimization. And some of the reasons to study decentralized optimization is to improve the scalability and the robustness and resilience, the flexibility and adaptability, and also privacy and energy efficiency. But that was just some short recap of, so that we're all on the same page here. And so let's start by picturing this graph here. And this actually represents an electrical network. And we call the graph G, and it has a set of vertices V from 1 to 5 in this case. The links in this graph are made up by symmetric random walks, and that means that moving from a point I to a point J equals moving from a point J to point I. So it also means that the probability of choosing to walk any of the roads connected to a vertex is equal, and also walking back on a node that we have already walked on. Okay, so now imagine a case of where we want to walk in this graph until we reach a subset S of the vertices in the graph. And then when we reach that subset, we finish walking. And if the vertex is I that we end up on, then we get a reward Vi. And we now want to know what our expected reward is from walking in this kind of graph. So firstly, we have the probability of moving from point I to point J, or vertex I over to vertex J, and that we get from the Markov chain transition probability. And that is defined as the transition rate or weight Yij. So that's the likelihood of going from the edge on the edge between vertex I and J, and then divided by the sum of the weights of all edges connected to J, where Ni is the neighbors of vertex I. Okay, so the expected reward Pi can then be stated by saying that if we start on a vertex that is in the set that we want to end up in, then the reward is of course Vi, or the same as the vertex reward. And if I is not in the set that we want to end up in S, then the reward is the sum of the expected rewards from I to each neighbor j, weighted by the probability of moving to that neighbor. Okay. By this example, you may think that adding a link in the graph is always beneficial. And so, for example, if we add a link between 2 and 4 here, we can create a new way to the potential optimal solution. So the statement that adding a link in a graph is actually true for a case of when we have an electrical network, since that would actually create a new way to where we want to go. But the statement does not go for all networks. And an example is a road traffic network. So here we have a scenario where 6 cars wants to travel from point S to a destination node N. The time or delay it takes for each car to travel depends on the number of cars on the same road. So these numbers represents the delay on that edge. Okay, so more cars in a road, of course, means a higher delay. Okay, we have a model here, a model that we call A, where we have 2 separate roads from S to N, and those are SWN and SEN. So here the Nash equilibrium formula actually says that the cars will split up in a balanced way. So 3 cars will actually go in one direction and 3 cars will go in the other. And that would optimize the system delay for all cars. So the system delay here would be 83 time units. Okay, but if we actually add a road, as in this model B, so we have added a road between W and E. Okay, so then we have 3 different alternatives of roads. So we have the same roads as before, but we also have a road that goes from SWEN. And intuitively, you may think that that would decrease the overall delay by providing an additional route for the cars. However, this is actually where the Brace paradox comes in. And the Brace paradox states that adding one road does not always make the cost smaller, since and this happens because the individual drivers are seeking the shortest route for themselves, and then they may choose the new road that we have included. And that would lead to a suboptimal distribution of traffic, where some roads become overburdened. And in this model, the introduction of the new road, as you can see, the delay on the roads actually became higher than for the model without the road. Okay. So that would bring us to a concept named the Wardrop equilibrium, which could potentially avoid the Brace paradox of happening. So here we have another network with some directed links between a set of nodes. And the routes can be described as a subset of links. So for example, to get from A to B, we would take this link 1. And to get, and to get from, say, C to A, we would have 2 alternatives. So we would either go on link 5, or we would do the other alternative of going on link 4 and then link 2. And the routes can then be described in a link route incidence matrix. So in this case, we have denoted the matrix A. And so for a case of a on the link J and route R. So if the link belongs to the route, then the number in this matrix will be 1, and otherwise it's 0. Okay. So the Waldorf equilibrium is all about creating what is called a stable routing pattern. So that means that no driver has any incentive to switch their path. So that would mean that every source and destination path SR for route R is larger or equal to the path we're on right now. So every driver is on their shortest source destination path. And this theory can be described mathematically by saying that we have a vector of flows along routes, so that X is the R, which is the traffic on the route R, and then R, and they belong to the possible routes through the networks. Then we can say, okay, so and then if the traffic on a route is larger than 0, then the sum of the delays with respect of the traffic on the link and then multiplied by the incidence matrix. So if the route or link is active, that would be equal to the minimum case of delay on that route as well. So what we're essentially saying here again is that every road is optimized so that all drivers are on their best possible path. Okay, so now that we have a little bit of background, let's get started with a simple setting of a decentralized optimization problem. In this setting we're in, so say we have some parameter vector x, which lies in our D. So it's a d-dimensional vector. And then let's say that we have some functions fi, which takes as input this parameter, a parameter x, and map it into R. So these fi's could, for example, be the loss function of a neural network parameterized by x and computed over different data sets I. So basically each fi could be a neural network loss function taken as input x over a certain subset of data, where the subset is I. Okay, so then our goal here is to that we basically want to find this minimum of the sum of all the fi's over x in this space RD. So we want to find the x star, we could say, that optimizes this sum of the different fi's. So the way we can do this is that we have some restrictions or conditions. And the first thing is that our data, I never talk for this long. Okay. All the different fi's are actually distributed across the nodes in our system. So we say that we have n nodes, and each of them only have access to their own fi. And the second condition is that every node can communicate with only its neighbors. And the neighbors are the nodes to whom it's connected to, where the connectivity is defined by some underlying graph structure. Okay, so let's take a look at an example graph that this could rely upon. So say in this case we have 5 nodes. Each of these nodes has access to only its own fi, or loss function, or whatever that would be. So the node 1 only has access to f1, node 2 only has access to f2, and so on. And no nodes has access to all fi's. in this case. So it's a distributed case, you would say. Okay, and then let's also say these nodes are connected somehow by a certain graph structure. So, for example, it could look like this. And one of the assumptions that is typically made in this kind of problem is that the graph is connected, which means that there exists a path from every node to every other node. And so, for example, if we had a node 6 up here, this would not be a connected graph. Okay, and then the idea is to basically somehow through these connections send information, which I said would typically be the current parameter estimate. So node 1 sends its parameter estimate to x1 to node 2, and node 2 would send its parameter estimate to x1, for example. And then we do this in every iteration of our calculation, and then and in this way we somehow want by every node taking a certain action over its own objective function, as well as communicating information to the nodes that it's connected to. So we want to, in the end, minimize this sum that we had. Okay. So now we can use this graph notation that we had and rewrite our objective function a little bit. So our initial goal was to find the x that minimizes the sum of all these i's. And we had also defined that the nodes are up to n in our system. And so now we can keep calling those nodes n, and we can define our graph G. So G would in this case be consisting of these nodes n and some edges curly e. So the edges are of course representing the connections between the nodes. And then we also need to denote this with xi, so the local parameter estimate held by the node I. And as we said, the setting that we're in, the nodes are willing to share some information, but they can't share their raw data with each other. So they can't share the FIs, which is why, again, let's see, so I don't say that. Exactly. So with this new graph notation, we can formulate this problem in the following way. So okay, we can say that our objective is now to minimize, again, the sum of the different FIs, but now evaluated for each xi, for each xi in the space RD. And then I being up to n, so the number of nodes that we have, and we additionally impose a condition that says that basically each xi would equal the xj for n for every ij in our set of edges. So if any two nodes are connected through an edge, we say that their parameter values must be equal. Okay, so let's talk about how we would actually do this kind of optimization, or one way to do it at least. So in the decentralized setting that we're in, there's no node that has access to all the FIs, but every node I has access to its own FI. So to make the notation more convenient, what we'll do is we'll define this interaction matrix A, which is defined as having elements Aij, where Aij is non-zero if Ij is an edge on the graph. So if I and j are neighbors. So for now, we don't really mention about the values that I Aij can take on. We only say that it's not zero if the vertices are not connected. Okay, so one option to define this decentralized optimization algorithm with gradient descent would be the following. So here we have 2 steps. In the first steps, what we basically do is from node I, we receive from all of our neighbors from whose this Aij is not zero. So then we receive their parameter estimate xj at iteration k. So k would be our iterations from 1 up to some t. And then in the second step, what happens is that the node I would update this average value k, xi k plus 1/2, and by taking our gradient step or learning rate. Maybe you can see that. Where the gradient is evaluated at this average value. So just a recap, so we have 2 steps. The first one is the mixing step, where each agent sends its, or node sends its current estimate to its neighbors and receive from neighbors their estimate. And then we have the gradient step, where nodes takes a gradient step over its local objective function evaluated at the parameter estimates after averaging. Okay. So we could get some intuition on what is actually happening here by looking at what's happening to the average parameter estimate value. So we define this as x bar k to be the average of all the different xi's in our system at time k. And then we can look at the dynamics of this x bar k. So if we just fill in the dynamics that we have for each individual node and average them, what we would get is the following. So here we would obtain this average over all the nodes in our system, since we're interested in the x bar k. And then the term, the blue term, is just comes from this xk plus 1/2 I. So that would say it's being the average from all the other nodes that it's connected to. And the next term is the same as we did here, but only the average value. Oh, sorry. Okay, so then we can rewrite this by sort of moving out this ji term. And then we can make this assumption that is very often made in these cases, and that is that the sum over I of aij is 1. So that would mean that in this case, that A is left stochastic. So that means that the columns sum up to 1. And then using that, we can rewrite this expression. So now we have aij equals 1. So then we get this in the end. And then if we were if we were to rewrite this algorithm using this gradient evaluated so we can include this this error term ek here, and that would be, in this case, it will look like that. And as long what we need to know here is essentially that as long as these EK terms are small, the solution will converge to the global optimum. And this explanation sort of gets to the core of how decentralized optimization functions. And so it's gradually guides the average of the guesses towards the optimal solution. And it achieves this by adjusting how fast or slow this process goes with the learning rate. Okay. So moving on to discussing some random access networks, which is a little less mathematical. In this example figure, we have multiple base stations that cannot communicate directly with each other. So instead, they have to contact each other through this satellite. So if a base station needs to pass a message to another station, it sends it via the satellite, and the satellite broadcasts it back. The issue here is called content resolution. So if transmissions from 2 or more stations are sent at the same time, then the messages will actually interfere and they need to be retransmitted. So the question here is, how can we avoid collisions like this happening? And how should the stations arrange their transmissions to the satellite? Okay, so there are a few approaches to solve this issue that might come to mind. The first one would be sensing when someone else is transmitting. And so if we could sense when someone else is transmitting, then we could completely avoid collisions by sort of waiting for a moment when the transmission lane is free. But the problem with this approach is that the finite speed of light causes a delay between the time where a station starts transmitting and the time when other stations sense this interference. And also, as the processing time increases, the speed of light will cause problem over shorter and shorter distance. The other approach would be to use a token ring. In this case, we would label the stations in an order to send their messages to the satellite in that order. And when a station is done with its transmission, it would send on the token ring to say that it's finished, and then let the next station in order start their transmission. And also, if the station has no messages to transmit, the token would just simply be passed on to the next station. The problem with this strategy is that if the token gets corrupted, so by ambient noise, for example, and it would also cause problems in a case of where there are very many stations and constant traffic. So simply passing the token would take a long time. Okay, so the third approach is to use a protocol solution, which I will go into now. So one widely used protocol to handle these types of issues is the Aloha protocol. The Aloha originally stood for Additive Links Online Hawaii Area, and as the name reveals, it was developed in Hawaii in 1970s. And its purpose was to enable communication between computers on different islands using radio broadcasting. And Aloha is a random access protocol that are implemented on the medium access control layer, the MAC layer. All users in Aloha compete for the same shared communication channel, and each user transmits data whenever they have data to send. So they never check if the channel is free, they just send data when they have something to send. But the purpose of Aloha protocol is to determine which competing station must get the next chance of accessing the multi-access channel at the MAC layer. But as you can imagine, with this strategy, there is still a big potential for collisions. When users are sending their data independently, there's a big potential for data packets to collide. So, and that would mean they get garbled. Started. Okay, so there are actually two ideas of the Aloha protocol. The original version says that any station, as we said, can transmit whenever they have data ready to be sent. So they never check if the channel is free, which of course increases the risk of collisions, but it also simplifies the transmission process. After transmitting data, the sender expects to receive an acknowledgement from the receiver confirming that the data has been successfully received. So if the sender does not receive an acknowledgement, it assumes that the data has been lost or there has been a collision. And then the sender waits for time to resend the data again. So this method is quite simple. When the network is not heavily loaded, it works quite okay, but it can lead to big inefficiency under heavy traffic, since it's a big potential for collision. So then they have actually improved this Aloha protocol a little bit, and they call this modified version the slotted Aloha protocol. And that is designed to improve the efficiency by reducing the likelihood of collision. So in slotted Aloha, the time is divided into discrete intervals and known as time slots. And each of these time slots has a duration equivalent to the length of the frame. Which is the data that's being sent. And when a station has data ready to send, it must actually wait until the beginning of the next time slot to transmit. And this helps to reduce the collisions because it decreases the window of time when collisions actually can happen. And despite these improvements, collisions can still happen in slotted Aloha, especially if multiple stations attempt to send data at the beginning of the same time slots. Okay, so looking a little bit at the throughput of the two variations of the protocol, we can see that the throughput for pure Aloha is given by S, which equals G times e to the power minus 2G, where G is the average number of frame transmission attempts per frame time. So the probability that a frame is transmitted without collision. And the maximum throughput in this case occurs when G equals 0.5, and that would translate to 18.4% efficiency. And in the case of slotted Aloha, the throughput is calculated with a slightly different formula due to the reduced vulnerability to collisions by time slotting. So the maximum throughput for slotted Aloha occurs when G equals 1. So that would yield a S max, or the maximum throughput, as 0.368, which is 36.8% efficiency. And that is one of the ways of showing that slotted Aloha is more efficient than pure Aloha. Okay. But there are, however, ways to improve the Aloha protocols even more. And one way is to include estimating the backlog. So the Aloha protocols do not have any knowledge of the backlog in the standard protocols. So a long backlog would actually cause or significantly lower the probability of a packet being transmitted successfully. And this is because as more stations attempt to send their data simultaneously, the likelihood of collision increase, which in turn leads to more packets waiting to be transmitted. So the probability of successfully transmitting a packet is quite small. If stations have the information regarding the backlog, they can adjust their retransmission attempts accordingly. So with this knowledge, the protocol could decrease the probability of retransmission during times of a high backlog. And here is a short example of estimating backlog. So here we have a case of where NT is the packages waiting to be transmitted, and F is a probability of a packet being transmitted, which is equal for all packages. And what we want to do is we want to find the optimal probability for a retransmission for a given backlog size. So we can start by defining the probability of exactly one transmission attempt given the backlog when the number of packets waiting to be transmitted equals n. So probability is then given by n times f times n f1 minus f to the power of n minus 1. Okay, so to find the optimal probability here, we would want to find the case that if the f that maximizes the chance of a successful transmission without collision. So then we can set the derivative of this probability with respect to f, and then set that to 0, and then we would yield a f equaling 1 divided by n. And so as the backlog n becomes large, the probability of a single retransmission attempt approaches 1 minus 1 divided by n to the power of n minus 1, which converges to e to the power of minus 1 as n goes to infinity. So if stations knew of the backlog, they can adjust their retransmissions probability accordingly. So by setting f to its maximum throughput, the throughput of the network can potentially be maximized, approaching e to the power of minus n. And as you might have noticed, this throughput is actually the same as the slotted aloha throughput, but that doesn't mean that estimating backlog would improve the slotted aloha even more, because the slotted aloha throughput is sort of an estimate throughput. So by estimating the backlog on slotted aloha, we would actually be able to get closer to that maximum throughput. Okay, so until now our discussion has assumed a scenario where each network connection either receives the full amount of the requested bandwidth or does not receive at all. But however, this is a simplification, and in reality, the bandwidth actually needs to the bandwidth needs of a connection can vary very much over time. So a bandwidth profile can be quite complex, and so rather than a constant stream of data, many applications have very unpredictable behavior. And this means that the peak bandwidth rate can be much higher than the average. Okay, so if we just allocate enough bandwidth to handle the peak rate all the time, it can lead to inefficiencies as much of the allocated capacity may go unused during the non-peak rates. And so the key question we need to address here is how can we achieve an acceptable balance between the capacity and still keep a low probability of packet loss. Okay, so here we also have a few different strategies. The first one would be to a full peak rate reservation. And in this strategy, each connection has its peak rate reserved as every resource along its path. And the advantage of this is that we ensure that there's no lost packets due to insufficient bandwidth. But it also requires a significant amount of capacity at the resources. And that is because the peak rate is often so much higher than the average. So that would lead to underutilized capacity, and the connection is not operating at the peak. Okay, the second way would be to have a mean rate reservation with queuing. And here the network would reserve the mean rate for each connection and then allow packets to queue if there are overloads. It's possible to stabilize the queuing network since not all connections will require their peak simultaneously, but it can result in a large delay in packet delivery. So especially if there are many connections experiencing peak loads at the same time. Okay, so what we would want here is sort of a hybrid strategy between 1 and 2. And that is what we're going to go into now. So to find that strategy in between, we'll start by introducing the Chernoff bound. So here we're looking at a scenario where we have a series of independent random variables, which goes from x1 to xn, and the sum of those is expressed as y. And here we want to find the probability that the sum of variables y deviates from its expected value by a certain amount. So then we can utilize a tool from probability theory called the log moment generating function, defined as m of s, where s is a real number and e denotes the expected value. And then we can use Markov's inequality, which provides us an upper bound for the probability that a non-negative random variable exceeds a certain threshold. And then we can find that the probability of y being at least as large as some constant c is bounded by the moment generating function on each x. Yeah, exactly. The moment generating function with respect to each x raised by n, and then divided by e raised to the power of sc. But to further tighten up this bound, we use the Chernoff bound, which optimizes the inequality over all positive values of s. So the Chernoff bound gives us a way to estimate the likelihood of a sum of a random variable significantly exceeding its expected value. So that is useful for when doing network congestion work. So we're very interested in the probability of traffic exceeding a certain threshold. Okay, so then we have the Cramer's theorem, where we have the same independent random variables, and there's some denoted by y. And here we can start by the assumption that the expected value of x1 is less than some constant c, and the probability, the positive probability actually of x1 being larger than c, yeah, that is, it's positive. And the Chernoff bound provides us with the probability that the sum of the variables are greater than 0. So that one that we got before. And then the Cramer's theorem takes this sort of a step further by considering the behavior of this probability as n approaches infinity. So when the y is very large. So this theorem states that the limit of the scaled up probability that the sum exceeds c is bounded above the infimum of ms minus cs for non-negative values of s. So if we have a large number of events, the Cramer's theorem would allow us to predict the likelihood of the sum y deviating from its expected value. Okay, so here is a short example just to get these two theorems in place. So here we have a single resource with a capacity of C, and it's shared among J types of connections. And the number of connections of type J is denoted as Nj, for J being 1 up to capital J. The total bandwidth demand S is the sum of the bandwidths of all individual connections, where Xij represents the bandwidth used by the ith connection of type J. The moment generating function for the bandwidth is given by the following. So the log of the expected value of e to the power of x, Esxij. And then using the Chernoff bound, we can establish an upper bound for the probability that the bandwidth demand S exceeds the probability capacity C. So for any S larger or equal than 0, the Chernoff bound is defined as the formula that we received before. And to find the tightest upper bound here, we seek the infimum of the right-hand side over all non-negative S. So then if this infimum is less or equal to a variable gamma, minus gamma, then we can say that the probability of the total bandwidth being larger than our capacity C is e to the power of minus gamma. Okay, and so this is sort of a way to quantify the risk of the total bandwidth, that the total bandwidth demand will exceed the available capacity. So by calculating this gamma, we can estimate the probability that the resource will be overutilized. Okay, so we're getting to the last slides here. So we're going to introduce just an acceptance region, which here is denoted by A, and that is defined for all the allocation of a resource with capacity C among J types of connections. So this acceptance region is actually the same formula as we have here. Like that. And it's set for vectors n in the non-negative real space Rj. That satisfies this condition. And this condition would ensure that the total expected load remains within the resource capacity limit, considering the gamma variable, which is sort of a safety margin. And for the case where J equals 2, that case is actually visualized here. So here would be our acceptance region in that case. And then again, we have Nj representing the number of connection types of type J. And by applying the Cramer's theorem, we can state that if the number of connections falls within the acceptance region, then the probability that the total bandwidth S exceeds the capacity C is at most is e to the power of minus gamma. So a new connection request can be accepted as long as adding its connection keeps the total vector N within the acceptance region. So finally, our aim was to ensure that the total bandwidth demand does not exceed the available capacity, while also remaining a low probability of overutilization. So here we have defined the effective bandwidth of a connection type J. So the effective bandwidth alpha on a connection type J of S is given by this formula. And so, and ms is again the moment generating function of the bandwidth with demands for connection types J, and S is a parameter that we chose to minimize the probability of exceeding the capacity C. Okay, so let's see. Okay, so to find the appropriate S for this kind of connections, we look for a point N star, which is on the boundary for the acceptance region. So there, that gives the infimum or the greatest lower bound for N, where N equals N star. So our admission control setup in this case for not overloading the resources in our systems would be to accept a new condition as long as adding its effective bandwidth to the total does not violate this probability of the capacity constraint. And this approach provides sort of a methodological way to manage network admissions while accounting for variability and stochastic natures of network. Yep, and that is all I had. Thank you.
Thanks a lot. We have some immediate questions. One? Or should I just point to someone asking a question? Seems that no one has a question, so it's crystal clear for everyone. Good. I assume most of you, if you never heard about the Cramer bound and these kind of and Chernoff thing, you're in serious problems. You need to read a course on it, because these things you will run into in signal processing, information theory, everything is centered around this. So you better know it and how to use it. I would also say that you probably seen through these two seminars that you're into the subject of computer engineering, computer science. That means you should also take courses in graph theory, because it's really connected into this. optimization is extremely important for whatever you do. So you better also learn optimization. And for those who want to learn more of multiple access protocols, I can strongly recommend the book by Raphael Romm and Moshe Sidi called Multiple Access Protocols, Performance and Analysis, which is like the god when it comes to books on random access protocols. It's heavy, but very informative. So I strongly suggest, if you're interested, you can ping me and I can send you a PDF version and you can dig into it. It's a very nice book with a lot of nice mathematics on different random access protocols. So for those who really work on wireless, these kind of things, I think you should take a read. It's very nice in that sense. So then I ask Amanda, do you see any use of this in your research, in your future research? I mean, you're in the first year, so do you see some of the tools in the queuing that can be handy for your future research?
Yeah, I do. We have discussed a little bit on creating some sort of project that relates to like how to queue the decentralized system, so the edge devices or something like that into a queuing theory scenario. So yeah, I think something like that I will apply.
Okay, then it has been useful.
Yeah.
It's important.
I mean, that was actually the question I was sort of thinking of as well. Like, how would you, I mean, looking at this, I mean, I guess maybe more of the first parts that you talked about might be more relevant for that case.
Yes.
Like how, but I think this is something we will discuss after this meeting when you as well. But
Yeah.
how do you see that you could use this for like your plan forward?
Yeah. So these, like all of these things that I've discussed today is, of course, applicable on queuing networks. So that is sort of the next step here. I had some slides on optimization of queuing networks and how to apply these methods that I didn't prioritize right now. But yeah, so that would be sort of the idea for my own work as well, to apply some sort of a queue of decentralized, decentralized system.
In many cases, when you see papers in literature, you see very simple queues. You assume for making the mathematics easier, but I mean, in reality, assuming a MM1 queue, I mean,
Yeah.
or especially if you go to more complex networks, you have to dive into this NG thing, you know, or even complex things. So it's good to have an understanding of different queuing models, presuming research in this area.
Yeah.
Good. So I strongly recommend people take the course in game theory. It's very nice. You also find it very common in financials. The guy Nash was a brilliant mind. It's really nice. Also, if you like the economical part in life, you can benefit from reading about Nash and his findings. It's nice. So anyway, thanks a lot, Amanda.
Thank you.
So thanks a lot for attending. I hope it was useful for everyone. See you.
Thank you.